In question 2, we're told the isotope of uranium, uranium-238, decays into a stable isotope of lead, lead-206, by means of a series of alpha and beta minus decays. In A, we're asked in this series of decays, alpha decay occurs 8 times, and beta decay occurs n times. We need to find n. Well, every alpha decay loses 2 protons. Every beta minus decay gains 1 proton. 8 alpha decays means 16 protons have been lost, but in going from an atomic number of 92 to 82, the net loss is only 10 protons. Therefore, we've gained 6 protons through 6 beta minus decays. In B part 1, we need to explain what is meant by the binding energy of a nucleus. Binding energy is the energy required to split the nucleus into separate nucleons. In part 2, we have a diagram showing the binding energy per nucleon for some stable nuclides. We need to use the diagram to estimate the binding energy in mega electron volts of the lead-206 nucleus. Well, reading off the graph, the binding energy per nucleon is around 7.88 MeV, and the nucleus contains 206 nucleons, so the binding energy is 7.88 MeV for 206 nucleons, giving 1620 MeV. In C, we're told the half-life of uranium-238 is 4.5 times 10 to the 9 years, which is much larger than all the other half-lives of the decays in the series. A rock sample, when formed, originally contains 3.0 times 10 to the 22 atoms of uranium-238 and no lead atoms. At any given time, most of the atoms are either uranium or lead, with a negligible number of atoms in other forms of the decay series. In part 1, we need to add to these axes graphs to show how the number of uranium and lead atoms in the rock sample vary over 1.0 times 10 to the 90. In part 1, we need to add to these axes to show how the number of uranium atoms and the number of lead atoms in the rock sample vary over 1 times 10 to the 10 years from formation. We need to label the graphs uranium and lead. Well, at the start, we'll have 3.0 times 10 to the 22 uraniums and no leads. After one half-life, we'll have 1.5 times 10 to the 22 uraniums and the same number of lead. After 2 half-lives of 9 times 10 to the 9 years, we will have 0.75 times 10 to the 22 uranium, and we'll have a number here which will make up 3 times 10 to the 22, so this would be 2.25. We can then add lines to both axes and label them. In part 2, a certain time t after its formation, the sample contained twice as many uranium as lead atoms. We need to show that the number of uranium atoms in the rock sample at time t was 2.0 times 10 to the 22. Well, uranium plus half as many uranium equals 3.0 times 10 to the 22. And so 3 uranium over 2 is 3.0 times 10 to the 22. Uranium then is 2 times 3.0 times 10 to the 22 over 3, which comes out at 3.0 times 10 to the 22. But it doesn't. Rearranging gives this expression, which comes out at 2.0 times 10 to the 22 as required. In part 3, we need to calculate t in years. Well, the number of atoms is the number of atoms at the start times e to the minus lambda t, where lambda is the decay constant. Lambda is given by the natural log of 2 over the half-life, and so we can rearranging gives this expression. We can then take natural logs of both sides, and the natural log of e to a power is just the power. Substituting in for this expression for lambda, we get this equaling minus ln2 times t over t to the half. We can then rearrange for t, putting in the values gives t at 2.6 times 10 to the 9 years.